Assalamu alaikum students. Hope you are all fine by the grace of Almighty Allah. Today is our second lecture and the contents of second lecture are forms of energy, mechanical energy, energy transfer by heat, energy transfer by work, heat versus work, first law of thermodynamics for closed systems. Okay, we will start from the forms of energy. Energy can exist in numerous forms such as thermal, mechanical, kinetic, potential, electric, magnetic, chemical, and nuclear, and the sum constitutes the total energy, which is represented by E of the system. We represent the total energy of the system with the symbol E. Total energy of the system on a unit mass basis is denoted by small e. It is the energy per unit mass, and the units for energy is kilojoule, and when it is divided by mass then its unit becomes kilojoule per kg. Thermodynamics deals with the change of total energy, that is del E or del small e, energy per unit mass, or you can call it specific energy as well. The concept of macroscopic form of energy and microscopic forms of energy was also discussed in the previous lectures as well. So in the macroscopic forms of energy, those a system possesses as a whole with respect to some outside reference frame. For example, kinetic and potential energy. Kinetic energy and potential energies are the macroscopic forms of energy. Microscopic form of energy, those related to the molecular structure of the system and the degree of the molecular activity. That is the microscopic form of energy. Internal energy U. Internal energy is represented with the symbol of capital U. The sum of all forms of microscopic form of energy. The sum of all the microscopic forms of energy is known as internal energy. You have to remember that capital U is the internal energy, and there is also a small u, that is capital U divided by mass. Okay. Kinetic energy. Energy possessed by the system as the result of its motion relative to some reference frame when all parts of the system move with same velocity. Okay, as we know that kinetic energy is due to the motion of the object, or the component of the system that are moving. So the formula for kinetic energy is half mv square, and the unit is kilojoule, and the kinetic energy per unit mass can be represented with by small ke, and we have multiplied the kinetic energy with mass, that is equal to small ke, and its unit is kilojoule per kg. Potential energy. Energy possessed by the system as a result of elevation in a gravitational field is known as potential energy. The formula for potential energy is mass into gravitational force multiplied by elevation. Z is represent to elevation. The unit for the potential energy is kilojoule. The potential energy per unit mass is represented by small pe, that is G into Z, gravitational force into the elevation, and the unit of potential energy per unit mass is kilojoule per kg. Magnetic, electric, and surface tension effects are significant in some specialized cases only and are usually ignored. So the effect of magnetic force, electric, and surface tension effects will be ignored in our problems. So now we know that there is an internal energy, kinetic energy, and potential energy. Therefore, this total energy of the system can be represented by this formula: energy is equal to internal energy plus kinetic energy plus potential energy, and their individual formulas are on the right hand side and the unit is kilojoule. Similarly, the energy of the system in per unit mass can also be written in this formula, and its unit is in kilojoule per kg. Most closed systems remain stationary during a process and thus experience no change in their kinetic and potential energy. So you have already studied about the closed system in thermodynamics 1, which usually remain stationary. But in control volume or open system, mass is continuously flowing in and out of the system. Therefore, they typically involve fluid flow for long period of time. It is convenient to express the energy flow associated with fluid stream in rate form. That is meant, rate means with respect to time. Therefore, mass flow rate equation is written here, and you know how it is derived. You know that density is equal to mass over volume, and then there is its derivation, which comes out rho 1 a1 v1 equal to rho 2 a v2. So on the right hand side you see a fluid flowing from the pipe, and the cross sectional area is represented by AC. D is the diameter of the pipe, and the fluid is flowing with an average velocity V average. And right hand side, the mass flow rate, from the continuity equation we know that mass flow is equal to mass which is flowing out. So the total energy of the system remain constant. So rho is the fluid density, A is the cross sectional area of flow, and V is the average flow velocity normal to AC. Here you must know that this is the volume flow rate. Okay, I will write it here. Okay, you should know that this is not velocity, this is volume flow rate, and that is velocity. So in the further slide, to ignore the confusion, I have written, I have changed the symbol of velocity to C. So students might get confused with the volume, specific volume, and velocity. So I have changed the symbol to C to denote the velocity. Okay, and similarly energy flow rate will be E dot is equal to m dot E. That is energy flowing inside the control volume will be equal to the energy flowing outside the control volume. Many engineering systems are designed to transport fluid from one location to another at specified flow rate. Uh, you know that the flow rate is mass flow rate represented by m dot, velocity represented by c, elevation difference represented by z. And the system may generate mechanical work in the turbine, or it may concern mechanical work in pump or fan during this process. So you know that in turbine the hot stream through the blades of the turbine, and in pump the pressure is increased of the fluid from P1 to P2. That's the low pressure fluid enters into the pump, and the pressure is of the fluid is increased many times. Such system can be analyzed conveniently by considering the mechanical form of energy only and the frictional effect that cause the mechanical energy to be lost in the form of thermal energy. You know that during any mechanical form of friction effect are also present, and friction force usually transform into heat. Mechanical energy, form of energy that can be converted to mechanical work completely and directly by the ideal mechanical device such as ideal turbine. So mechanical energy can be converted into mechanical work. It means 100% we can convert mechanical energy into mechanical work, such as through the device like ideal turbine. So if we have 100 joules of mechanical, then it will 200 joule of mechanical work. However, this case is not possible for thermal energy. In the later section, we will come to know that 100% thermal energy cannot be converted into mechanical work, whereas 100% mechanical energy can be converted into mechanical work. Next is kinetic and potential energies. These are the familiar form of mechanical energy, which we have discussed in the previous slide as well. A pump transfers mechanical energy to a fluid by raising its pressure. So it's the working of pump that it raises the pressure of the fluid flowing through it. And turbine extract mechanical energy by dropping its pressure. So turbine and pump are the opposite form of mechanical devices. Pump raise the pressure, whereas turbine drop the pressure. We have to supply energy. The pump, we have to supply energy as input to the pump to raise the pressure of the fluid, whereas turbine give out energy by dropping the pressure of the fluid that is flowing through it. Pressure of the flowing fluid is also associated with the mechanical energy. Unit of pressure is Pascal, and that is the conversion, different unit of Pascal as well. So energy per unit mass, so that is pressure and that is specific volume. So you know that density is equal to mass over volume. So volume is equal to mass over density. Volume equal to 1 of, so specific volume equal to over density, which is written here. Pressure itself is not a form of energy, but a pressure force acting on it through a distance produced called work in the amount of P over rho per unit mass. Uh, you know that PV is equal to P rho, since specific volume equal to density. So the PV flow work is denoted by P over rho. P over rho. So the flow work energy, this is the total amount of energy. This is due to the pressure force. This is due to the velocity, or you can see that it is a specific kinetic energy. This is the specific potential energy. I will write it, kinetic energy, and that is potential energy, specific potential energy. So the total energy is represented by, total rate of energy is represented by capital E. I will remove that. Capital E, it's a rate, energy rate, mechanical, which is equal to mass flow rate into energy, that is specific energy. So we have multiplied that with mass flow rate, and rate energy of a flowing fluid is represented by mass flow rate to workflow, kinetic energy, and potential energy. It is a sum of all forms of mechanical energy. So the change in mechanical energy of a fluid is incompressible. Rho is equal to constant for incompressible fluid flow per unit mass. So what are incompressible fluid? Liquid and solids are considered as incompressible fluids. Liquids and solids. So change in energy is represented by pressure change, velocity change, and change of elevation. Flow work difference of energy, kinetic energy difference, and potential energy difference. And the unit of change of energy is kilojoule per kg. Now rate of mechanical energy change of fluid during incompressible flow. So you will have to only multiply this equation by m dot. So you can find the rate mechanical energy of fluid during incompressible fluid. So when you multiply that equation m dot, so the units become kilo joule per kg, multiply kg per second. So kg will cancel out, it will be kilojoule per second and to kilowatt. Mechanical energy of fluid does not change during the flow of its pressure, density, velocity, and elevation remain constant. Mechanical energy change represents the mechanical work supplied to the fluid if change of mechanical energy is greater than zero, or extracted from the fluid if change of energy is less than. Mechanical energy on the right side, this is a picture of turbine, and this is a generator, this is a turbine, water flowing from this, that is the reservoir, water flowing stream and exiting through the turbine from here. So in the absence of irreversible losses, the maximum produced power rate of work is known as the power is proportional to the change in water surface elevation from upstream to downstream. So the maximum produced power is equal to the change in the kinetic energy into the mass flow rate. The elevation is represented by h here, and mass flow rate into gravitational force. So the maximum work obtained from the turbine can be calculated as the change in water surface elevation from upstream to downstream. That is upstream and this is downstream. The change in the elevation will give us the maximum work produced. This is the close-up view of the previous diagram. Here you can see the close-up view of turbine, that is point 2 and that is point 3. We know about the turbine that it is a power generating device which produced power by dropping the pressure of the fluid flowing through it. It extracts the energy from the fluid passing through the turbine. So that is, this is the row. To close up, maximum produced power is proportional to the drop in water pressure from just upstream to just downstream of the turbine. The pressure will be dropped when the fluid passes through the turbine blades. So the pressure at point 2 is P2 and pressure at point 3 is P3. So the pressure at point 2 will be greater than pressure at point 3. So the delta P is the pressure difference, that is the density, and when it's multiplied with the mass flow rate flowing through the turbine, that also gives the maximum power. Energy transfer by heat. Heat, form of energy that is transferred between two systems or a system and its surrounding by virtue of temperature difference. So as discussed previously, temperature difference is the driving force in the thermodynamics. Heat is the energy in transition. In thermodynamics, the term heat simply means heat transfer. So you can see that there are 3 cans of soda, as you can see in this picture. The temperature of first can is 25 degrees centigrade, the temperature of second can is 15 degrees centigrade, and the temperature of third can is 5 degrees centigrade. Whereas the temperature, ambient temperature or room air temperature is 25 degrees centigrade. So the heat will flow from warm body to the cold body, that is heat flows from room into the soda bottle. So the amount of heat that flow into 5 degree centigrade bottle is 16 joule per second. The rate of heat flowing into the 15 degree centigrade soda bottle is 8 joule per second, whereas uh, no heat will transfer in a soda can of that is at 25 degree centigrade. So it is mentioned here the temperature difference is the driving force for the transfer. That is very important sentence and usually asked in MCQs as well. The larger the temperature difference, the higher is the rate of heat transfer. So as you can see that the temperature difference between the room air and this soda can is maximum. That way the rate of heat transfer is scenario. Whereas in the second can, the rate of heat transfer is 8 kilojoule, that is lesser than the first one, and there is no heat transfer in this case, third case. Okay, system boundary, that is a closed system. Energy can cross the boundaries of system in the heat and work. Energy is recognized as heat transfer only if it crosses system boundary. So the energy can be transferred into the system in the heat and work. Either it can the system is allowed to reject heat or gain heat, or it's allowed to gain work or heat in a closed system as well. A process during which there is no heat transfer is called adiabatic process. So you can adiabatic system, and that is insulation. This insulation will prohibit all the heat, no entering or out from this system. There are two ways a process can be adiabatic. Either the system is well insulated so that only a negligible amount of heat can pass through the boundary, or both the system and surrounding are at the same temperature and therefore there is no driving force. Temperature difference for heat transfer is zero. So it is saying that either you have an absolute insulation which prohibit all the heat transfer, or the temperature difference, if the temperature difference is zero, then there will be no heat transfer and the system is said to be an adiabatic system. Q is equal to delta Q is equal to 0. So you know that the adiabatic system is that in which there is no heat transfer. Even though there is no heat transfer during an adiabatic process, the energy content and thus the temperature of system can still be changed by means of such as work, turbine and pump. So you must remember, if you asked, the turbine and pump are adiabatic devices. Heat transfer mechanism. There are mainly three modes of heat transfer: conduction, convection, and radiation. Conduction. Conduction is of heat transfer to solids and stationary fluids. With convection is the process of heat transfer the fluid in motion, and radiation the transfer of energy due to emission of electromagnetic waves. So you must remember that for first and second the medium is necessary, whereas for third no medium is required. Okay, formal sign convention. Heat transfer to the system and work done by the system are positive. So heat transfer to the system, that is the system, and work done by the system is also positive. Heat transferred from the system, heat is going out, and when on the system, it is worked on the system, are negative. So Q in is positive, Q out negative. Q in negative and W out is positive. Alternative to convention is to use the subscript in and out to indicate the direction. So you can use the subscript Q in, Q in, W out. So no, it is written Q in. The sign with Q in will be positive, and it is written heat is rejected by term. The sign with the Q out will be negative. It is done on the term. The sign with the Q in written that work is obtained from system positive. The work is obtained, so that filter is done on the compressor, so the sign is negative. So work done per unit mass of the system can be written as W small w is equal to capital W divided by mass. The unit of work done per unit mass is written as kilojoule per kg. Work done per unit time is called power when it is noted by W dot, and the unit is kilojoule per second. Power is the work done per unit time that is represented in the form of by the unit of kilowatt. Path function quantities which cannot be located on graph by a point but are given by the area. Point function when two properties locate on the table, those properties are called as point function. So this is state 1, that is state 2. So like temperature, pressure and volume, you can state that at state 1 pressure is P1, volume is V1, temperature is T1. Similarly at state 2 the pressure is P2, volume is V2 and temperature is T2. But path function like example is heat and work. These are two example of path function that required the path followed by the process from reaching state 2 from state 1. So the path A have different values for heat and work, and for process B that start from state 1 to state 2 have different value of heat and work. Both heat and work are boundary phenomena. Both are associated with a process, not a state. Therefore, both are the path function. Their magnitude depend on the path followed during the process as well as the end states. Path function have inexact differential designated by the symbol partial. Differential amount of heat and work is represented by partial Q and partial W respectively instead of dq and dw. As volume is a point function, therefore it can be represented by delta V, change in volume from state 2 to state 1 or from state 1 to state 2. Volume change during process 1 to 2 is always the volume at state 2 minus the volume at state 1 regardless of the path followed. Whereas you cannot calculate heat and work with del H or del W. That is incorrect. The first law of thermodynamics for a control mass undergoing a cycle. For a cyclic process, that is the symbol for cyclic process, and partial Q is equal to partial W. Mathematically, the first law is expressed as integration for cyclic process partial Q is equal to integration cyclic process partial W. So the first symbol cyclic process integration of partial heat transfer is cyclic integral for heat transfer. Represent the net heat transfer during the cycle, whereas integration cyclic partial W is the cyclic integral of work. Represent the net work done during the cycle. So what is a cyclic process? We have already discussed that is state 1 to state 2. If the process goes back to its initial state, then it is known as cyclic process. When a system undergoes a thermodynamic cycle, then the net heat supplied to the system from its surrounding plus the net work input to the system from its surrounding must equal to 0. From first law of thermodynamics, this is the mathematical form. These are two separate processes. First from state 1 to 2. Through process A, the state will change from 1 to 2, and through process B, it will come back from state 2 to 1. And in the second, the change of state from 1 to 2 is through C process, and then again coming back from 2 to 1 through process B. So through by first law of thermodynamics, partial QA plus partial QB is equal to partial WA plus partial WB. For the second process, partial QC plus partial QB is equal to partial QC plus partial QB. Both are equal as they are both the cyclic process. Therefore, the first law can be implemented on them as you can see. So subtracting the second of these equations from the first, you can see that QB will be cancel out, and QA minus QC is equal to WA minus WC. The quantity Q minus partial W is the same for all process between state 1 and 2. So if we make many processes from state to 2, the value of partial Q minus partial W is the same for all the process between state 1 and 2, and the value partial Q minus partial W depends only on the initial and final state, as not on the path followed between the two states. This value is constant for all the processes between state 1 and 2. Therefore, we can say that this is a point function. Because E is the property, its derivative is written as dE. So dE is equal to partial Q minus partial W. As you can see that this is a function, whereas those are path function. So therefore the function written as dE here, and path function we have to use partial sign with those because they are inexact differential, whereas point function are exact differential. Therefore you can find value at the state. So the energy at state 2 will E2, one is E. So their value can be calculated by partial Q, which is equal to the heat rejected again when it's going from process to my work done or obtained when it is going from process 1 to 2. E1 and E2 initial and final values of the energy of the control mass Q1 to transfer to the control process from state 1 to 2, and W1 to 2 work done by the control mass during the process. So the next topic is regarding the ideal gas equation. This is known as the ideal gas equation. PV is equal to N R bar T, where R bar is the universal gas constant and it can be converted into specific gas constant. The relation PV is equal to MRT. The important points to remember are active forces between the gas molecule is negligible. Attractive force is negligible. Volume of individual particle is negligible as compared to the air volume of the gas. Okay. Hypothetical gas or ideal gas obey this law at all temperature and pressure. This equation PV is equal to MRT is also known as the equation of state, where M is the mass gas, R is the characteristic gas constant for the particular gas, where R bar is the universal gas constant. The value of R bar is 8.314. Okay, this characteristic constant can be calculated by this formula. R is the characteristic gas constant, R is the universal gas constant, and M molar mass of the gas. For air, the molar mass is 20 and the gas constant is 4 divided by molar mass. The characteristic gas constant for air is 0.287 kJ per kg Kelvin. Student must remember this value and will be used later on in the problems as well. So there is isochoric process. What is an isochoric process? A constant volume process. When a gas is stored in a rigid container, say that it is an isochoric process. So we will apply the isochoric process to the ideal gas equation or equation of state that we have just discussed in the previous slide. P is equal to T. So all the values that are constant will be we will put them on the right side. So P we will write because it is constant. So when that is constant, so we can P1 over V1 is equal to T1 over T2. In the PV diagram for isochoric process, it is a straight line parallel to y-axis. Isobaric process. Isobaric process is constant pressure process. For equation of state, V is equal to mR over T into V is directly proportional. V1 over V2 is equal to T1 over T2. In a PV diagram, the isobaric process is a straight line parallel to x-axis. Isothermal process. It's a constant temperature process. T is equal to constant. So the equation of state is reduced to PV is equal to mRT, right side is constant. So P1 V1 is equal to P2 V2. In a PV diagram, it is this type of curve. It's shown on the right hand side. Adiabatic process. No heat enters or leaves the system. dq is equal to 0. The equation for adiabatic process is PV gamma is equal to constant. So P1 V1 power gamma is equal to P2 power gamma, where gamma is the ratio of specific heat at constant pressure to the specific heat at constant volume. We will discuss about this in the later slides. What is specific heat and what is its contribution in the open system. So Tv gamma minus 1 is equal to constant, therefore T1 over T2 is equal to 2 over 1 gamma minus. So now this is here we give the next portion. So these are to remember. That the result of these derivation we will use in the problem solving. In thermo 1 you have already derived all these equations, therefore I am not going into the details and just discussing the result of these derivation. So polytropic process. What is a polytropic process? It's a general process which lies between the isothermal and adiabatic process. Is denoted by small n. Generally, the value of n is lies between minus infinity and positive infinity. But during our discussion, the value of n will be between 0 and gamma. What is gamma? Gamma is the adiabatic index that we have discussed in the previous slide. The value of gamma is the ratio of 3. So P1 V1 power n is equal to P2 V2 power n. Therefore, T1 over T2 is equal to V2 over V1 power n minus 1. This is the same derivation that we have in the previous slide. We have just replaced the gamma with n. So therefore the same results are obtained to the derivation. So instead of here you can see that uh, that is the in the previous slide, that is p21 minus gamma, which is replaced by p21 minus n. So this PdV work or displacement work transfer. In thermodynamic, work is done when the boundary of the system may expand or contract. So this is a piston Anderson as shown. So at state 1 the piston is to the left and volume is reduced and pressure is increased from 1 to 2. So you can see that at 1 the pressure is lower, whereas its pressure is increased and volume is decreased as well. Sign convention: work done by the system is positive. Example, turbine. Work done on the system is negative. Example, heat pump and compressor. So work done for isochoric process. Isochoric process is a constant volume process. In thermodynamics, the work transfer through constant volume process is zero. So work for constant volume process is zero. This is an important statement which may be asked in the MCQs as well. Mathematically, that is change in work done or work done is equal to PdV. So change in volume is equal to 0. Therefore, work is 0. And PV diagram we have discussed in the earlier slide as well. It's a straight line parallel to y-axis. Work done for isobaric process. Work done for isobaric process. It's a constant pressure process. Therefore, the volume is changing, and the work done is equal to P into V2 V1. Work will be represented by this portion in PV diagram. That will be V2 V1 and P. Work done for isothermal process. So isothermal process is a constant temperature process. So the work done is represented by P1 natural over P2 equal to, as P1 we can raise by MRT, because this is a constant temperature process, natural log P2. These derivation are included in Thermo 1. Therefore, I am not driving these relation. I am just discussing the result of these processes. Work done for polytropic process. N is the polytropic index as we have discussed. So therefore, work done is represented by P1 V1 minus P2 V2 over N minus 1. As on the right hand side you can see the PV diagram of the polytropic process, where you can see the pressure and volume change, polytropic index. Work done for adiabatic process. Gamma is the adiabatic index, and work done for adiabatic process is equal to T1 T2 over gamma minus 1. Similarly to the polytropic process, adiabatic process is shown on the right hand side on the PV diagram. The change in the pressure and volume is, you can see them done can be calculated for both. Isothermal versus adiabatic curve. For isothermal process, left hand side; for adiabatic process, right hand side. So for isothermal process, PV is equal to constant. Initiating the above equation, P dV plus V dP is equal to 0. So Tp over dV shows the slope of isothermal process, and on the right hand side, PV gamma is equal to constant differentiating the above equation, and we get the slope of adiabatic process. So that is the slope of isothermal process. This is the right hand side, that is the slope for adiabatic process. So you can see that the slope of adiabatic process is equal to gamma times the slope of isothermal process. The above expression shows that the slope of adiabatic curve is greater than isothermal curve. That is, adiabatic curve is more than isothermal curve. This is the important statement, and from MCQ's point of view, you should remember that the slope of adiabatic curve is more steeper than the isothermal curve. The expression for polytropic index is given as, so as the polytropic index, and the expression for polytropic index is given as n is equal to log P1 over P2 divided by log V2 over V1. Therefore, we now calculate the value of for different processes. For isobaric process, the value of is 0. Similarly, for isochoric process, the value of n is infinity. For isothermal process, the value of n is 1. For adiabatic process, n is raised by gamma, n is equal to gamma. So now these are the different curves shown in on PV diagram. I want you to pause the video and just answer which curve depicts which process. So the first curve depicts the isobaric process where n is equal to 0. It's a constant pressure process and is a straight line parallel to x-axis. For isothermal process, n is equal to 1. That is the curve for polytropic process, and adiabatic n is equal to gamma. So as I have said earlier, polytropic process is general process which lies between isothermal and adiabatic process. From the curve you can know that this process lies between isothermal and polytropic process. And the last is isochoric process where the value is infinity. Isochoric process is a constant volume process which is a straight line parallel to y-axis on PV diagram. So you have and there are two lines. So you will have to calculate the steeps of the curve. So this you will know that that is an adiabatic curve and that is thermal curve.